Very good. Welcome back. In this lecture, we're going to be studying a few of the consequences of the maximum entropy method, and we're going to be commenting on on various important features that, unless you get them right, you might actually misuse the method. So let me go to my tablet, and so this is what we had seen last time. The maximum entropy method is a method to update from a prior to a posterior. And the way you do it is you maximize this relative entropy. So in other words, you rank all potential probability distributions. You rank them according to some preference. And then you maximize the entropy. You choose the one that's ranked the best, subject to the information that is supplied in the form of constraints. So this is the general strategy. What is it that we prefer when we rank probabilities P relative to a prior Q? Well, the functional form of the entropy is designed basically to value prior information. This is what makes the method Bayesian. When you care about what it is that you have learned in the past. The actual design of the entropy is accomplished by having two basic design criteria. One is that what I've called here the locality for mutually exclusive subdomains. And what that means is that if you have information about some subdomain D prime that does not overlap with the subdomain D, then the posterior conditional on D is not updated. The posterior coincides with the prior. This is what I mean by we value prior information. If in the information you received there is nothing to tell you how these guys should be changed, how those probabilities should be updated, then you don't. The reason a design criterion like this is very, very powerful is that this is supposed to be true for all choices of the subdomains. And so it's not like you just have one condition here. You have an infinite number of conditions. This is the criterion that leads to the entropy taking the form of sums of functions of x. So that form, that particular shape of the entropy functional comes from DC1. The second one is the fact that we value, in science, you have to value independence. You have to agree that if you do not receive information about correlations, the method of inference itself, namely the entropy, should not introduce correlations into your problem. And what that means is that if you have two subsystems and you update one with information I1 into a posterior and you update the other with a prior Q2 with information I2 to another posterior, and none of this in the first case has anything to do or is there any reference to the other one, then the update of the joint prior with both pieces of information that involve that are completely independent should lead to an independent posterior. This is what leads to the log function here. Very good. So what we want to do now is we want to analyze or discuss various touchy points with this function for the entropy. So first one, how do you pick priors? Well, there are two answers to that. One of them is by analogy to physics. How do you pick initial conditions? Do you have a theory for when you're going to solve equations of evolution in physics? Do you have a theory for picking what the initial condition is? And the answer is no. What the laws of nature or the laws of physics are all about is how you change from one state to another. From one to another, there is always the beginning, and the laws of physics do not tell you what the beginning ought to be. So the same thing happens with priors. The laws of inference do not tell you what your prior beliefs are. You come with that, and then you proceed. That is fortunate and unfortunate. It's fortunate because it actually is telling you what it is in this whole process of inference that's extremely objective. It is the process of updating, not the process of assigning a prior. Sometimes you can assign a prior from considerations of symmetry. For example, when you have a situation where you have no reason to prefer one microstate over another, you may want to say, well, my state of ignorance is highly symmetric. It does not favor any microstate. I'm going to therefore assign them a uniform distribution. Perfect. When you are in that situation, that's the way to proceed. Most of the time, that's exactly what's going to be happening. You have to look in your problem for some sort of symmetry and proceed. Yet a third way is the old method of hope and pray that your choice of prior didn't make a difference. Sometimes we're fortunate, sometimes the information in the form of in the constraint is so overwhelming that the prior does not matter. That's very fortunate, but of course, it's not necessarily the case. Typically, this happens when you have some kind of central limit or some large n situation. Then it really doesn't matter what your prior was. You just proceed with the information you have, and you get a unique answer. But you have to be very careful here, because sometimes that is the case. You have a large n. The thermodynamic limit, for example, in thermodynamics works so well because you have something like this operating, like C. But in other situations, or the classical limit in classical mechanics, same thing. But this is not always the case. And then when you're trying to discuss rare events, so for example, if you're discussing earthquakes, or you're discussing catastrophes like that, or you are discussing the detection of dark matter, or something that is very rare indeed, under those circumstances, the data will, of course, provide you with valuable information. But because the data is so rare, it's not like you're going to get an incredible amount of data. Then your inference is going to be guided by your prior probability distributions. Your prior information takes an incredible amount of importance. And, well, you have to be very careful there, because your prior information when you're doing new science is precisely the kind of thing that could go wrong. But in any case, under those circumstances, the prior is absolutely dominant. So you have to be careful. Here is another interesting remark. So here's a comment. What if the prior vanishes in some region? So Q, for some domain vanishes. If you go back to our formula for the entropy, you see that you're going to have a little bit of a problem, because if the Q goes to 0, the log goes to minus infinity or something like that, right? It diverges. So let's take a look at that. Let me write out that formula first. So you have minus the x p log p plus the x p log q. And so clearly, if in a particular region or for particular values of x, q is equal to 0, the log of 0 is like minus infinity. And what this happens is that any probability distribution P, any P ranked relative to Q will get a really bad ranking. You will never be able to assign a posterior because the posteriors are all awful, right? Unless, this is the interesting point, any P will ranked relative to a Q that's vanishing will get the entropy going to infinity, minus infinity, unless the P in that same subdomain vanishes too. So let me rewrite this here. Relative to a Q that vanishes in some region will get infinitely badly ranked unless the posterior vanishes as well. Now, this is interesting because what it's telling you is that if you assign a prior of 0, you will not be able to update that prior to a posterior, no matter what constraints you put. This is the same issue that we had met back in the very beginning of the course when we discussed how Bayes' theorem Bayesian updating, remember how that worked? The posterior for a parameter is the prior multiplied by, here we're going to have the data, and here we have the likelihood function then, and then here we have some normalization constant. Okay, so this is going to be something like that. Very good. Look at what's going on here. If you have a prior that's 0, you're going to get the posterior that vanishes as well. So both the method of maximum entropy and Bayesian updating lead you to the same conclusion. If you're so extremely prejudiced that you assign a probability of 0, there is no way that any amount of information in the form of constraints or in the form of data will allow you to change your mind. So you have to be very careful. So a prior that vanishes cannot be updated. So that's the first comment. Be careful with induction. If you have a prior that vanishes, make sure that really you believe that. Very good. There are two other things that I would like to discuss concerning this that have to do with consistency. Sometimes, so the method of maximum entropy, ME, allows updating. But sometimes you can update without using the method of maximum entropy. sometimes you can update purely using probabilistic arguments. So we have to be able to check that those probabilistic arguments and the method of maximum entropy agree with each other. So this is an important consistency check. Okay, let me write it just to make clear what it is I'm doing here. Sometimes purely probabilistic arguments, purely probabilistic means without using entropy, allow updating too. And if they allowed you to update, you have to make sure that your maximum entropy method and these special cases agree with each other. Otherwise, you have an inconsistency, and that is the ultimate sign of irrationality, and so that's really not allowed. One example, this is a really important one, is when you have central limit theorems. I'm not going to discuss this in any detail. You can look up the argument in the textbook. It goes under the name of, let's see, it's section 6.4, consistency with the law of large numbers. It is actually really nice to see how you can, with purely probabilistic system arguments, when you have a large number n of subsystems, then the kind of predictions and inferences you're going to draw are completely in agreement with the method of maximum entropy. In fact, this ends up being important. And this agrees with ME. And the reason that this is important is that many people have come up with alternative axiomatizations for what entropy should be. And the forms of entropies that you get need not have the log. So, for example, there are a variety of entropies that depend on parameters, eta, and so these entropies allow you to define a quantity associated to two probability distributions, a measure of the separation between the two, and these entropies are, this is just an overall factor in front for convenience. It's not particularly crucial, but then you have a dx, a coefficient. Eta is just a constant, something like 0.5 or 0.3 or 0 or 1, p plus, or actually, let me draw my eta better, minus, then there is eta q, and then there is another term here that's minus p over q to the power eta, and now we finish. Okay, very good. This is a generic form for entropies described by Amari. Sunichi Amari is a really important Japanese statistician. We're gonna have more to talk about him in the next few lectures when we discuss information geometry. Some of the advantages of an object like this is that it allows you to establish a sort of like a separation or measure a separation or the divergence between two probability distributions. The probability distributions need not be normalized. You can see that if these guys were normalized, then this term would be pretty boring. It's just a constant and then the integral of p. Same thing with the prior. So this allows you to go beyond normalization. Then you have dxp, which looks very much like a regular entropy. But then you have instead of having log p over q, you have p over q to a power. When eta goes to 0, you recover in the limit as eta goes to 0, you recover the regular log entropy. So this is a generalization of the standard log entropy. Very good. These forms of this type have been discovered by a number of people. Renyi, a Hungarian mathematician, Salis. Salis is an interesting guy. He's a physicist, and he's come up with forms of the entropy that look like this too. It's very, very popular. People discuss those very much. Salis is a little bit like me. I think he's originally Greek. Then he was, for a while, he was Argentinian. And now he's Brazilian. He's been in Brazil for many years. So a little bit of a nomad like myself. In any case, what's wrong with an entropy like this? Well, one of the things that one can immediately say is that if you write an entropy like that, which is not of the form that we had up here, then you must have violated some of the design criteria. In other words, we designed entropy to satisfy certain criteria, to perform a certain function. So the question that should be asked is, when you write a different form of entropy, what are you violating? Well, what you are violating in that particular case, for eta different from 0, when you don't get the log, is you're violating DC2, the criterion that the updating should not introduce correlations that were not implicit either in the prior or in the information. So this is where these guys go wrong. They do introduce, inadvertently, they will introduce correlations into the picture. Another thing that goes wrong with these guys here is that they are inconsistent with the central limit theorem. So if you have alternative ways, to make inferences that do not involve an entropy, then, like central limit theorems, large N, then they will be inconsistent with this. The only entropy that's purely consistent for the purposes of updating is the log entropy. So what one could say, to be fair to the pretty nice mathematics that arises from formulas like this, what one can say is that these objects might be convenient measures of a separation between Q and P. They may be useful for other purposes, but not for the purpose of updating. For the purpose of updating, they do not work because they introduce all sorts of unwarranted correlations. So there we go. Consistency. Yes. Is your entropy consistent with the law of large numbers? Crucial check. Here is another one. There is another situation where we can use purely probabilistic arguments to do the updating from a prior to a posterior. We saw that. And so one of them that we saw towards the beginning of the course was Bayesian updating itself. So what I would like to discuss next is Bayesian updating as a special case of maximum entropy updating. So how does that work? Let us recall how Bayes works. When you want to do Bayesian updating, what you're trying to do is you're trying to do an inference about a parameter theta. So we want to infer theta on the basis of, well, three things. One of them is prior information, the prior. B is information on some collected data, the data. And finally, if you want to draw conclusions about theta on the basis of x, it is absolutely crucial that you understand how theta and x are related. So you need a likelihood function, the relation between x and theta. The first crucial consequence, or rather comment, that one has to make in a problem like this is that the actual space of variables that you're talking about, what if we try to be a little bit pedantic, we would say the universe of discourse, what it is that you're talking about, is not just the space of thetas, capital theta, or so neither that nor the space of possible data, but the whole, the joint space. And the reason is that when you're trying to set up your problem, not only you do not know what theta is, which is what is reflected in the fact that you have the prior. You do not know what theta is. So this space here, the space of thetas, must be included in what you're talking about. But also, you do not know what the data is, right? You don't have it yet. So the space of x's is crucial as well. So the whole space must be incorporated. So what we're talking about as the prior is not just this object, but this object, namely the joint distribution of x's and thetas. That is what the prior is. So when we try to now maximize an entropy, this is the object that we have to take into account. The entropy is an entropy in the joint space. By the way, this is the most difficult part of the whole derivation, figuring out what it is that you're talking about, what you're going to be integrating over when you discuss what an entropy is. Then you have the allowed posteriors. Then you have px theta. And then here you have the joint prior. So that's the first step in trying to figure out how it is that you do Bayes' rule as an example of maximum entropy. Make sure you have the right entropy. Make sure you integrate over the correct space. Now, what is the constraint that we're going to be putting here? So next, we have the prior. Now we have to figure out the constraint. The constraint is that when you look at the possible posteriors, the possible posteriors we can write them as, we can always use the product rule and write the posterior as the probability of x and then the probability of theta given x. Now, what we know is that of all the possible probability distributions for x, which is what we would get when we marginalize, this is going to be let me see, what we know about the posterior. This is going to be the constraint. We're going to look at all possible posterior probabilities such that when we take the joint and we marginalize and get rid of theta, this is going to be something that has complete certainty about the actual data. So this is the constraint. We know x has to be equal to x prime with certainty. The posteriors have to satisfy that constraint. Very good. So let us put this into the maximum entropy calculation. So we're going to say that the variation dx d theta, let me put the joint, the log of p. Here we're going to put the joint prior. And now we're going to say, okay, we would like these guys here to be normalized. So let me just cheat to figure out remind myself what Lagrange multiplier I chose, alpha. And then here we're going to have the integral dx d theta p minus 1. So I'm just adding 0. This is normalization. And then we're going to put another constraint, let's call it lambda, that takes this into account. So we're going to put that constraint, here goes, d theta px theta minus delta x minus x prime, like so. But now we have to be careful here. You see, there is an x prime here. It appears that I have written here one constraint. Px, the probability of x, is equal to this delta. But in fact, what I have written is not just one constraint. I have written an infinite number of constraints here. I have written a constraint for every single value of x. For most of those values of x, what I have on the right-hand side is 0. For the value of x when x equals x prime, I'm going to have an infinity. So this is an infinite number of constraints, one for each value of x. So you see, the constraint here has a parameter x, a parameter x. So this is many constraints. And so for each constraint, I have to introduce one Lagrange multiplier, and I have many of them. So this is what the full constraint maximization is going to look like. Close that, set that equal to 0, and we're done. Now it's a matter of computing. So let's do it. When we do the maximization, I'm going to vary delta p, and so there is going to be a log p over q. Log p over q multiplied by delta p with a minus sign. Very good. I'm not going to write the delta p, okay, nor those integrals. The delta p's are all going to be independent, so I'm just going to write the coefficients. So I vary this delta p, this p here. Now I'm going to vary this other guy here, and what I get when I vary that guy, I get 1 over p that cancels this guy, and then there is delta p. So this is going to be a -1. Then there is in this delta p, this adds an alpha multiplied by the delta p. Then I vary these guys here. You see there is a dx and the theta, very much like you have it over there and over there. Oops. This is the theta. Okay, so there is a delta p, there is a lambda x. This is a plus lambda x delta p, and all of this is equal to 0, which means therefore that whatever this posterior is going to be, which this is the chosen posterior, this is going to be, let me see, I just cheat. This is going to be, did I P equal Q? Yes, this is going to have the Qx theta. Get this guy onto the other side, get the P, and then you have the Lagrange multiplier e to the lambda x, and the e to the 1 minus alpha and all of that is just going to be some kind of normalization. And we call that z, e to the 1 plus alpha. So this is what updating according to maximum entropy is going to look like when you have a prior Q and you have a constraint at every point x. So now we're done. What we have to now figure out is what is z, what is that Lagrange multiplier alpha, and what is lambda, what are those Lagrange multipliers that go with the data constraints. So in order to do that, we just say the multiplier lambda is determined from the constraint, like in all maximum entropy calculations, Lagrange multipliers are determined from the constraints. I hope that by now you start really becoming a little bit tired of me repeating always the same words, right? You maximize an entropy subject to the constraints, you introduce Lagrange multipliers, the Lagrange multipliers are determined so that the probability distribution satisfies the constraints. It's always the same routine. In this particular case, the constraint is up here. So let me just box it because this is what makes the ME method reproduce Bayes' theorem, in addition to the entropy being in the space x theta, okay? So it's determined from the constraints. So what we're going to do is just take this probability distribution here, integrate over theta, yes, and equate that to delta. So here we go. We're going to integrate marginalized theta, which is the same as marginalizing theta, e lambda x over z equals delta x minus x prime. Very good. When you look at something like what I have here, you see that this object here is just, this is a function of x. This is z is a constant. There is no theta here. So the integral can be done. This guy here is just take the prior and you marginalize thetas. So this is just the prior probability for x. And so what this means is that whatever these guys are, this has to be equal to delta x divided by qx. Let me substitute this expression back here. Back there. So I'm going to substitute that back there. And the result is that and I substitute e to the lambda. That's what I get. But if you divide this guy here by the q, what you have is q x given, I'm sorry, what do I get? Let me just do it slowly. I get qx q theta given x all divided by qx and then delta x minus x prime, which implies that px theta is equal to x minus x prime q theta given x. Because this is 0, unless x equals x prime, I can always put a prime there. So this is the conclusion, and if you were to write this, this is the posterior. And if you write this as the new, just using the product rule, what you have is that the probability is going to be that the probability of x is the delta, the probability of the theta given x is the old value. So it did not get updated. So what we see here is that indeed the method of maximum entropy implements minimal updating, which is how we had derived the Bayes rule in the beginning. So conclusion, if you integrate to find p theta, you integrate this px theta over all the x's. The delta function makes the integration trivial, and what you get is the old Bayes rule, which is written here. Conclusion: the method of maximum entropy is completely consistent with Bayesian updating. So not only is the method of maximum entropy, as I have defined it here, with those design criteria that lead to the log entropy, consistent with the law of large numbers, it is also consistent with Bayesian updating. It's good to have all of these consistency checks, because after all, remember, we're going to be using entropy to do inferences, to do inductions in situations where we really don't know what we're talking about. We have incomplete information. You have to know that at least this part of the framework is rock solid. One of the great advantages of having this insight into what the method of maximum entropy, how the method of maximum entropy is consistent, it's compatible with Bayesian updating, is the following. Remember how we started all of this? Let me go back to page. Whoa, what happened here? I've done something. Okay, now I'm in trouble. Okay, wait a minute.